Everyone, and welcome to our second installment in our Stream Health and Stormwater series. Just a reminder, we are recording the webinar today and it'll be posted to our website so you can review it in the future. We'll be addressing any questions you might have at the end of the presentation. So if you have a question, feel free to type it in that chat box at the bottom center of your screen, and my coworker Rebecca will make sure your questions get asked at the end. My name is Amy Miller, and I'm the watershed specialist for the Allegheny County Conservation District. Here is a look at the topics we're going to cover in our Stream Health and Stormwater series over the next few weeks. If you haven't registered for the remaining events, you can still do so on our Eventbrite page. Today's webinar is entitled Evaluating Stream Health, What to Look For. So as the title suggests, we're going to be discussing ways the citizens can tell how healthy their stream is. So just a quick recap of topics that we discussed in the series introduction on Tuesday. The first thing we looked at was the anatomy of a stream. Doing that, we defined several terms that'll be brought up throughout the series. Those terms included headwaters, or the source or beginning of a stream, the bed, banks, and floodplain, the parts of the stream. The floodplain is the area next to the stream, and a watershed, which is the area of land that drains to a common point, such as a stream or a lake. Secondly, we talked about stream dynamics and how streams meander or curve. Outside bends of the stream have faster moving currents that cause erosion, while the inside part of the bend has a slower moving current, which results in deposition of sediments. Then we talked about how stream health does not just involve the stream itself, but the whole watershed, including upland areas, riparian areas, and the floodplain. And lastly, we introduced some ways that human activities have influenced stream health. So in this webinar, we're going to take a closer look at stream health and specifically the things we can do to gauge how healthy the stream is. So to do this, we're going to take a deeper look at those physical, biological, and chemical properties that I mentioned on Tuesday, and why and what they can tell us about stream health. As a reminder, physical properties require us to look at the watershed as a whole, including the landscape surrounding the stream, its bed and banks, as well as the water. Biological properties tell us what is living in and around the water, such as macroinvertebrates, fish, and plants. Finally, chemical properties tell us what's in the water itself. So let's get into some of those physical properties and what they can tell us about streams. Typically, when evaluating physical characters of streams, we use a visual assessment tool that allows us to look at the big picture of the watershed as a whole while simply ranking each piece individually. And then we'll take the average of those individual scores to get an overall stream health ranking. There are up to 16 elements in the USDA protocol for visual assessments to evaluate streams, but you don't have to use all 16. Not all of them probably apply to your stream. That's because the protocol was developed for use nationally and not all streams are the same throughout the country. So each element is ranked on a scale of 1 to 10, or 0 to 10, with 10 being the best score and 0 being the worst. So we'll talk about some common ones that can be applied to your stream. And as part of the follow-up to this webinar, I'll provide some additional resources and to further explain the protocol and go over each of the elements individually. So we'll start with the riparian zone. Keep in mind the function of the riparian zone that we talked about on Tuesday, filtering sediment and reducing pollution by slowly releasing water, stabilizing stream banks, and slowing flood velocities. And you want to ask yourself if the riparian buffer that you're evaluating can perform those functions. That'll help you when you're ranking your buffer for visual assessment. Also, you can see here there are descriptions that'll help you distinguish between a 10 in this case, where the natural vegetation extends to active channel widths on each side, and say an 8 where the natural vegetation only extends one active channel width on each side. The active channel width is considered the part of the stream that is wet. Any terms that you may not be familiar with are explained in the protocol as well. You can also select a 9 if you feel it's somewhere in between, so you don't have to only choose the numbers that are listed in the description. They're just there as a guide. Now, visual assessments are somewhat subjective, so you should be able to justify why you ranked something, say, an 8 versus a 6. And I find that pictures and notes always help with this. And also, if you're doing it with a partner, talking it out can help as well. So I've included some pictures on a slide to accompany descriptions of the things you might see. The picture on the left, I would probably rank a 10 for riparian buffers. There appears to be a good amount of natural vegetation on both sides of the stream. It varies in size from herbaceous material to trees, and it extends back through the edge of the picture, so I assume that's at least 2 times the active channel width. So the middle picture, I would probably rank a 6. There appears to be good vegetation on one side, but if you look close, there's a building or a wall on the right side, so that wouldn't have the same amount of cover on both sides of the stream, which would decrease its ranking. Finally, the picture on the right, I would probably rank a 1. Lawn does not really equal natural vegetation in this case, even though some of it next to the stream is taller. If the pavement was right next to the stream, I would probably rank that as 0. So next is nutrient enrichment. If you remember from Tuesday, excess nutrients can rob a stream of dissolved oxygen, which is detrimental to the fish and other aquatic organisms that live there. You can virtually assess the stream nutrient levels, visually assess the stream nutrient levels by looking at the amount of macrophytes or aquatic plants in the stream. Again, there are general descriptions for the different rankings. So water is clear with some aquatic plants and very little algae, like the picture on the left. Then the reach score would be a 10. If it's fairly clear with some moderate algal growth on the rocks, you could get a 7. And finally, if it's really green with abundant algal mats, you'd want to rank that a 1 or a 0 for nutrient enrichment. Just remember, the more you look at streams and the more you do this, the better you'll get. But as long as you can justify your rankings, they're not necessarily wrong. So let's look at one more element, water appearance. The water should appear very clear with great visibility at least 3 feet of depth to score a 10. If the water looks like the middle picture, the ranking could depend on whether there were recent rains. If there were, you probably get a higher ranking, but if it looks like that all the time, the ranking would be lower, I'd say like a 3. And then the picture all the way on the right obviously has some pollution issues. That's an AMD discharge, which would decrease your visibility. Obviously you have some coloration in the water, and you probably have a strong odor at that site as well. So that would decrease your ranking for water appearance. So the best way to learn this is by doing. So I'm going to try an example with you guys. So take a look at this picture and evaluate it for water appearance. Type what you think the ranking would be and why in the chat box. I'll give you a couple minutes to do that. That's good. I'm getting a lot of ones in the box there. That's probably what I would give this. It's very turbid. You can't see any visible depth objects at visible depth. It's considerable cloudiness. This is an AMD discharge as well for aluminum. So there's obvious water pollutants in the water here. All right, so let's take a look at this one and rank it for riparian buffer. What do you think about this one? It's good. I'm seeing a lot of 8s, 9s. Yeah, I would rank this pretty high. It looks like there's varying sizes of vegetation there with trees. As far as you can see along the edges in the picture, it seems to extend out pretty far. So yeah, I would rank this pretty high. And one more, we didn't talk about invertebrate habitat as one of our examples, but if you look at the cover types below the rankings, you can see some examples. So if it was a 10, there'd be at least 5 types. 7 would be 3 to 4 types. So what would you rank this for insect or macroinvertebrate habitat based on the cover types listed there? How many can you see in the picture? Yeah, good. I'm seeing a lot of high numbers there. I see everything from the fine woody debris. There are some undercut banks with some overhanging roots there, different sized rocks, and cobble and boulder. So I would give this a 9, 8, 9, somewhere in there as well. So for those 3 examples that we just looked at, when I did this and I added up my score, I got a 19. So to get your visual assessment score, you add those 3 elements together and you would divide by 3 in this case because we looked at 3 categories, and that gives you a 6.3, and that puts you in the fair category for this stream. Now obviously this was a fictional stream with pictures from 3 different streams, but I wanted you to be able to get a look at some different rankings and see how to do this. So next, let's look at the biological properties. In wadable streams, fish are usually sampled via electrofishing or a backpack shocker. You have to have a scientific collector's permit to do this, so it usually involves working with a local university or a government entity like DEP or the Fish and Boat Commission. But if you're interested in what fish are in your streams, you could try using just a regular minnow trap, as long as you have a valid fishing license and follow Fish and Boat Commission guidelines. However, most biological assessments of streams involve macroinvertebrates. And we talked about kind of why that was on Tuesday. They're in the stream all the time, they can't really move, and they're good indicators of water quality. So when you're sampling macroinvertebrates, if you're just curious about what's in your stream, you can do hand collection. That just involves picking up some rocks and looking under them, looking in if there's kind of leaf pack material, you can go through that and find some different kinds of macroinvertebrates. But if you're going to assess macroinvertebrates for stream health kind of thing, you actually have to sample them with a net. So we use either a D-frame net or a kick net. Both types of nets involve kicking up the substrate or the stream bottom to dislodge the macroinvertebrates and send them into the net, which is situated downstream of the kicking. So then you would pick out your macroinvertebrates and identify them. and record them. There are many resources available to help you identify macroinvertebrates, like this dichotomous key. They ask very simple questions, and based on your answers, you move down to the next level. So like the first question is, does it have a shell? And then based on your answer, you would move down to the next question and so on until you get to actually what your macroinvertebrate is. So the whole purpose of using macroinvertebrates to assess stream health is based on their pollution tolerance. Some species are very sensitive to pollution and will not be found even when there's only a little. They are only found in streams with good water quality, and these are categorized into group 1. Group 2 are species that are moderately sensitive to pollution, meaning they can tolerate a little, but not a lot. These species are found in streams with good to fair water quality. And finally, group 3 are considered pollution intolerant, meaning that they can live just about anywhere. And these species are found in any water quality, but if you only find these species, it typically means the water quality is probably not very good. So once you identify them, you'll kind of group them based on their sensitivity, and again, I'll follow up with some forms for that if you're interested. And once you've done that, it's just a little math, and then you'll get your water quality score, which you see at the bottom there. And then you can compare that and determine the quality of your stream based on the macroinvertebrates. So finally, you can look at the chemical components of the stream. On Tuesday, I talked about the 6 water quality assessment components. Today, I'll talk about some measurements of these components and their ideal ranges in the stream, and some factors that might influence them. So for example, turbidity is a measurement of suspended particles such as sediment in the water. It's a measurement of the amount of light that's scattered when you shine a light through the water sample. So the more suspended solids in the water and the murkier it seems, the higher the turbidity will be. So the ideal turbidity range is 0 to 10 NTUs, or nephelometric turbidity units. Basically, the lower the NTU equals, the better the water quality. So the picture shows increasing levels of turbidity and their corresponding NTU values there at the bottom. Turbidity is mainly increased by land disturbance, be it through construction, mining, agriculture, or urbanization. These activities increase sediment and other suspended particles entering the stream. If the turbidity remains high enough for long enough, it can impact the amount of light aquatic plants receive and inhibit their growth. And as the base of the food chain, this effect works its way up to other aquatic organisms. Nutrients, typically we measure those via nitrogen and phosphorus compounds. They are essential for aquatic plants and animal life in the right quantities. So large concentrations of nutrients can have adverse effects on stream health. Ideal nutrient ranges for nitrogen are less than 10 milligrams per liter and less than 0.1 milligrams per liter for phosphorus. So fertilizers, manure, plant decay, and stormwater runoff are major non-point sources of nitrogen and phosphorus. Another source of nutrients, particularly nitrogen, is atmospheric fallout from burning fossil fuels, and then it enters the stream through either rain or snowfall. As I mentioned, increases in nutrients in the stream result in increased plant growth and algal growth, and this leads to decreases in oxygen that's available for aquatic organisms. Finally, the third measurement over there is temperature. So we know temperature is a measurement of how hot and cold water is, but water temperature has direct and indirect effects on nearly all aspects of stream ecology. So ideal temperatures of streams depend on whether it's considered a warm water stream or a cold water stream. In warm water streams, temperatures shouldn't exceed 89 degrees Fahrenheit. In cold water streams, they shouldn't exceed 68 degrees Fahrenheit. So while there's some exceptions, most of our streams in Allegheny County are considered warm water streams. The amount of oxygen that can be dissolved in water is partly governed by temperature. So as cold water can hold more oxygen than warm water, certain species of aquatic invertebrates and fish with high oxygen demands like trout are found only in cold water streams. Temperature also influences the rate of photosynthesis by algae and aquatic plants. As water temperature rises, the rate of photosynthesis increases, and provided there's the adequate amount of nutrients, this can lead to explosive plant growth and algae blooms. We talked a lot about dissolved oxygen levels already, but it is a parameter that's often measured. Dissolved oxygen levels should typically be at least 5 milligrams per liter or above to sustain life in the stream. Some species like trout, though, do have higher oxygen demand, and you'd want those dissolved oxygen levels to be above 6 milligrams per liter. Factors that affect dissolved oxygen are temperature, like we talked about, nutrients, and agitation. So as it flows over rocks in the water, that agitation creates more oxygen in the water. When the dissolved oxygen drops below 3 milligrams per liter, even hardy fish will die. Decreases in DO can cause major shifts in the kinds of aquatic organisms found in water bodies. Species that can't tolerate low levels of dissolved oxygen, such as mayflies and stoneflies, will be replaced by more pollution-tolerant organisms, such as midges and black fly larvae. Nuisance algae may also become abundant in waters with low dissolved oxygen levels. So then I want to talk a little bit about pH. pH is a measurement of acidity of a solution. On a pH scale of 0 to 14, 0 is highly acidic and 14 is highly alkaline or basic. A pH of 7 is considered neutral, and most organisms can only tolerate a pH that's somewhere close to neutral, usually between 6 and 9. If the pH is too high or too low, it can be extremely harmful. So what causes increases or decreases in pH in streams? Acid rain is something that's an issue in our area. It enters streams and can decrease the pH of a stream, making it more acidic. In general, an increase in pH is usually attributed to lime. So like geology, if you have limestone streams, they have a higher natural pH than other types of rock. Lime is also used in fertilizers, manufacturing of paper, glass, sugar refining. We don't have a lot of that here, obviously, but runoff wastewater from these industries can lead to increases in pH of a stream, making it more alkaline. Areas with, like I said, a lot of limestone geologies may have more alkaline streams naturally. Changes in pH can again shift those species found in streams, so moving further away from neutral pHs changes the species composition from to those more tolerant of pollution. Changes in pH can also affect how chemicals react in water. For example, ammonia is in a more toxic format at a higher pH than it is at a lower pH. So to truly assess water quality, you have to look at water chemistry, like these previous examples. However, they typically involve the use of meters and test kits and training that you may not have the time or inclination for. But if you'd like to become involved in stream sampling, I'd encourage you to get involved with your local watershed group. If there is one in your area, we have 11 active groups in Allegheny County. They're listed there. If there isn't a group in your watershed area, you can either contact ACCD or your local conservation district, and we can help you with either starting your own group or connecting you maybe with a neighboring group that you could work with. So again, if the water chemistry tests are a little more involved than maybe your life permits, there are a couple things that about the appearance of water that can tell us about water quality. The color and odor of water may give you a solid lead as to what's in it. It may determine when you should do further chemical testing. Well, I hope you don't come across many of these. Some of these pictures offer a pretty good idea of what may be in the water. Chemical tests would still be needed to confirm any of these though. So things you could see, a rainbow sheen like the top left picture. This could represent just iron oxidizing bacteria, which is natural, or oil discharges from runoff. To differentiate, if you trail a stick through the film, if the film readily breaks apart into small clusters, it's likely bacteria. If it swirls together, it's likely some oil-based discharge from runoff. If the water appears gray or has a strong odor of sewage, like the top right picture, could indicate a possible sewage overflow. And while both pictures on the bottom are white, they indicate very different things. The one on the left has a sudsy appearance, usually associated with detergents such as residential or commercial car washing, while the one on the right does not have suds and is most likely due to abandoned mine aluminum discharge. I do caution that streams do become naturally discolored occasionally. This can result from like iron oxidation, as in the top left picture, an algal bloom, as in the bottom left picture. Pollen on stagnant water can make it look yellow or green in the early spring or summer, as in the upper right picture, or tannins from fallen leaves, as the lower right picture, can make it look tea-colored, but it's usually still clear. So to really help with any of the types of evaluations we looked at, there's a number of citizen science tools available to assist with stream health evaluation. Some of the more popular phone apps are listed here. They can assist with everything from how to identify macroinvertebrates and plants to looking at and reporting water data in your area. They're also a great way to get kids involved in the outdoors. There are a number of issues that should be reported to a proper entity if you come across them while they're in a field. If you see a spill or a chemical discharge, it should be reported to your local authorities as well as DEP. Any exposed utility lines should be called into the utility company or the line owner if you can see a marker indicating whose line it is. Exposed lines can also be reported to DEP as well. Fish kills should be reported to the regional office of the Pennsylvania Fish and Boat Commission, as well as DEP. And any sediment from active construction sites should be reported to your local conservation district. Finally, I just want to emphasize that safety is always the #1 priority. So your safety and the safety of others is way more important than stream evaluation. So be smart, use common sense when looking at streams, avoid high flows in bad weather, and always let someone know where you're going. I hope you'll join us next week on Tuesday for the 3rd installment in our series, Sediment, Public Enemy #1. We'll discuss the #1 pollutant to our waterways, sediment. As I mentioned earlier in a presentation, we'll follow up this webinar with an email that contains links to resources that I talked about for evaluations. as well as a survey for the webinar series. Please take the survey. Give us your thoughts on how we can improve these outreach events, any future topics you'd like to hear about. We do try to incorporate your feedback and ideas into future events. So thank you for listening. That concludes my presentation, and I will now take any questions that you may have had.
Okay, great. Thanks, Amy. We have two questions. I think this is relating back to the visual assessment. What about a stream bank full of Japanese knotweed?
Well, it's not the greatest, but it is still vegetation, and it does still help the stream form some of those functions of a riparian buffer. I probably would drop the score a little bit because it is invasive and it doesn't necessarily provide the most stabilization for your stream banks.
Okay, our second question. Are there any fine-grained data spatially or temporally on streams in Pittsburgh?
Specifically within the city of Pittsburgh, that gets a little difficult. A lot of them are culverted, so they're in pipes. But any data that's available is probably through either the local watershed group or DEP. I don't know that there's exactly one-stop shopping for any kind of water data. It's usually done, like I said, through either a volunteer group or a local government entity like DEP.
So if there aren't any more questions, last call, we can wrap this up and look for a follow-up email from us.
Thanks everyone, and we'll see you back on Tuesday, hopefully.